All right, this is video 13 for the baby real analysis series. And in the last video, we proved that the product of the sequences an times bn converges to the product of their limits, a times b. And then we also proved that the convergence implies bounded for a sequence. So I'm going to leave it to you as an exercise to prove the limit law where you have the quotient of an divided by bn converges to a divided by b. And of course, b can't be 0, and then the sequence bn can't be 0 for all n. All right, so that's left for you as an exercise. I'm going to move on now to the Squeeze Theorem, go over the thought process behind the proof, and then the proof of the Squeeze Theorem. And then we'll end this video with the Monotone Convergence Theorem. All right, and Squeeze Theorem. So this is just the regular Squeeze Theorem with sequences from your calc class, but don't remember, it says if you have the sequence where Bn converges to A and sequence Cn converges to A, and then for some capital N in the natural numbers, whenever little n is bigger than capital N, we have the sequence An sandwiched in between sequences Cn and Bn. In that string of inequalities, Cn less than or equal to An, less than or equal to Bn, then it follows that the sequence An converges to A also. All right, so I think for me, intuitively, this makes sense. I mean, you're bounding a sequence An in between two sequences in which those two sequences converge to the same limit. So therefore, what's the sequence that's sandwiched in between must converge to that limit. So for the strategy, we wish to show, because of convergence of An going to A, that means that the absolute value of An minus A is less than epsilon for all n bigger than capital N for some capital N in the natural numbers. Both Bn converges to A and Cn converges to A. So there's some capital N where for all little n bigger than capital N, both Bn and Cn are within epsilon of the limit A, meaning you just have the distance from Cn to A is less than epsilon, and the distance from Bn to A is less than epsilon. So combining this with the assumption that we have Cn less than or equal to An less than or equal to Bn, it would make sense that the sequence An would also have to be within epsilon of A once we've reached this point for the index to be bigger than this capital N, in which Cn and Bn both converge to A. But to prove this formally, we need to consider whether the An term is smaller than A or larger than A. So suppose we're past the cutoff point for capital N, in which both Cn and Bn are within epsilon of A. And suppose that for some little n bigger than capital N, we have An less than or equal to A. So the nth term being less than or equal to the limit point, I guess, A. This is a picture of what it would look like. So again, we're at the point little n bigger than capital N. And so for the nth term, we see that An is less than the dashed line for A. So since we have Cn less than or equal to An less than or equal to Bn, that's why you see the purple dot of Cn being below An, and then An being below the green dot for Bn. And then in the red dashed lines, you have the limit A minus epsilon, so your epsilon amount below the limit, and then A plus epsilon, above the limit. And so visually, yeah, so An is definitely within, is definitely an epsilon within A because Cn is, since it is above Cn, which Cn is also within epsilon of A. Now for the case if the nth term an is bigger than or equal to the limit point a, then we'd have this picture. And so we have the green or the gold dot an above the red dashed line for the limit a. But since we have bn less than or equal to an less than or equal to cn, we still have an to be less than bn, which means that an is still epsilon within a because bn is within epsilon of a. So we're going to essentially combine these two cases to form this string of inequalities that a minus epsilon is less than an, which is less than a plus epsilon, which implies that you have the absolute value of an minus a less than epsilon. All right, so visually that's what's going on here. Now we're going to make this formal. All right, so the proof, given epsilon greater than 0, note 1, since Cn converges to A, there exists a capital N1, so that for all little n bigger than capital N1, we have the distance between Cn and A to be less than epsilon. So that inequality with the absolute value, that means negative epsilon is less than Cn minus A less than epsilon, which we can write that as A minus epsilon less than Cn, which is less than A plus epsilon, and I'm calling that star. All right, so graphically, for both cases, we have Cn in between A plus epsilon and A minus epsilon. Note 2, since Bn converges to A, there exists a capital N2, so that for all little n bigger than capital N2, we have the distance between Bn and A to be less than epsilon, which would imply that A minus epsilon is less than Bn, which is less than A plus epsilon. So in both pictures, you see that the green dot Bn is within epsilon of A. So now we're going to choose n to be the maximum of these two. We want n to be the maximum of these two index values so that we guarantee the convergence of both limits. Right? We've done this in previous proofs where we had to pick the max. So if capital N is the max between n1 and n2, and let little n be bigger than n, we combine this with the fact that Cn is less than or equal to An, which is less than or equal to Bn. And we combine that fact with the left half of star, so the left half of star, with the right half of double star. And that's where we get A minus epsilon less than Cn, which we know Cn is less than or equal to An, so that comes from star. And then because it's An is sandwiched in between Cn and Bn, then we have An is also less than or equal to Bn, and then Bn is less than epsilon or A plus epsilon, which comes from double star. All right, so this comes from star. This comes from double star. So just focusing on the sequence An, we have the sequence An in between A minus epsilon and A plus epsilon. So then we could subtract A, and we get negative epsilon less than An minus A less than positive epsilon. And that implies the distance from An to A, which is the absolute value of An minus A, is less than epsilon. And that's what it means to converge to the limit. So An converges to A. All right, that's the proof for the squeeze theorem. You probably could have made it a lot, maybe shorter than this, but I don't know. I like to make my proofs a little bit more, they're probably way more descriptive than necessary, but for me, will get like redundant sometimes, but I think the more I write, the better my understanding is. But as for sake of, I guess, beauty in math, you would want your proof to be concise, which this isn't necessarily concise, but at least it's, I think any ambiguity, it leaves out the ambiguity. Okay, so next I wrote down just more facts with limits. And I'm not going to prove all of these. I will prove just one of these, the square root one. So these are some facts that we're going to assume from here on. So if we have an converges to a, that means the absolute value of an converges to absolute value of a. And then the limit of n raised to 1 over n equals 1 if n is bigger than 1. Now if we have b less than 1, so it's a fraction between 0 and 1, or any real number between 0 and 1, then you have the limit b to the n is 0. Now if c is positive, then c to the 1 over n equals 1. And then this other bullet point, so if a is positive, then the limit of 1 over 1 plus n times a is 0. And then the two bullet points that we most commonly use, an converges to a, the square root of an converges to the square root of a, and similar for the squares. All right, and now I go over the proof for the for this one. All right, so we're going to assume an converges to a, prove the square root of the nth term an converges to the square root of a. And the strategy is going to involve the following. So we want essentially the distance between the square root of an and square root of a to be less than epsilon. That's what we want. And that happens we need to find that capital N, so that for all little n bigger than capital N, we have this result. So I start out with the absolute value of square root of an minus square root of a. Now, there's an algebra trick. I'm multiplying it by 1. And the 1, right, square root of an plus a divided by square root of an plus a is 1. But I'm writing 1 in a clever way so that we get the following. And that is the conjugate, right? Square root of an plus a is the conjugate of square root of an minus square root of a. So that when we multiply the numerators, we get the square roots to go away. And then you have just an minus a. The denominator is the square root of an plus square root of a. So that is the result after we multiply the numerators, since they're conjugates. Basically, it's the difference of squares. Now you could separate this, so this would be less than, the top part is square root of a, absolute value of an minus a. And that's going to be less than if you were to divide by just square root of a, right? Because here, you're dividing by a bigger value. Than if you were to do it here. Also, this is important, is that we only incorporate just the square root of a as a fixed number. We don't want to incorporate our sequence a in. Okay. Now the objective is we want this whole thing, we want the whole thing to be less than epsilon. right? And since we know that an square root of a, or since we know an converges to a, we can manipulate the top part, meaning we can make this as small as we like. And the question is how small? It's going to be small enough such that the distance from an to a is less than epsilon times the square root of a. That's how small we're going to need it to be. And we can do this because we know an converges to a. So it's going to happen for any epsilon that the distance between an and a is going to be less than that value. So this is like using a epsilon star, for instance. That's for all epsilon. So pick epsilon star to be epsilon times square root of a. So we're going to find the index capital N such that we have the distance from an to a to be less than epsilon times square root of a. All right, that is how small we're going to, that's how we manipulate our known distance based on, so that we get the whole thing to be less than epsilon at the end. So the proof, to let epsilon be greater than 0, find this capital N so that for all little n bigger than capital N, we have the distance from an to a to be less than epsilon times the square root of a. And again, we can do this since we know an converges to a. So it's always going to be true that the distance from an to a is less than any epsilon. So pick epsilon to be epsilon times square root of a. So hence for little n bigger than capital N, we have the following. So all of this was the same as above that I was doing in the scratch work. And then all of this is what we had up above. And essentially, since we know that the square root of an minus a is less than epsilon times a, then, so we know that is less than epsilon times square root of a, then the whole thing is less than epsilon times square root of a divided by square root of a. And that way the square root of a's cancel each other and you just get epsilon. Okay, so that is the proof for that one. Now I'm going to move on to a different topic, but still sequences. Now I'm going to talk about monotone sequences. And monotone sequences, you can either be monotone increasing or monotone decreasing. So for all n in the natural numbers, we have the terms xn less than or equal to xn plus 1, then the sequence is monotone increasing. So we just have like x1 less than or equal to x2 less than or equal to ... and so forth. So the previous term is less than or equal to the next term. So then for monotone decreasing, it's going to be greater than or equal to. So the previous term is bigger than or equal to the next term. All right, so that's monotone decreasing. Now, if a sequence is monotone increasing or monotone decreasing, then it's just monotone. All right, this shouldn't be anything new here. Again, this is from calc course, but we want to show this is the meat of the video. So we want to show the monotone convergence theorem. So say you have a sequence A and that's monotone. So it could be either monotone increasing or monotone decreasing. Then this sequence converges if and only if it's bounded. Further, if the sequence is monotone increasing, you either have the sequence xn diverges to positive infinity, or you have the limit of the xn equal to the supremum of all of the values from the sequence xn. So the supremum of the set of the values from the sequence is the limit of xn if xn is increasing. And that comes from because the sequence to be bounded. Now, if it's not bounded, then xn could diverge to positive infinity. So similar thing with decreasing. If it's not bounded, it goes to negative infinity. But if it is bounded, then the sequence limit, xn, converges to the infimum of the set of all the terms from that sequence. Okay, so before I do the proof of this, I'll go over some prerequisite knowledge and then some examples of what it means to be diverging to positive infinity or diverging to negative infinity. Just to recall that a sequence xn is bounded if there exists some capital M bigger than 0, where the absolute value of the terms of xn is less than or equal to capital M. All right, that was what it means to be bounded. Recall that in one of the earlier videos, I dealt with the sequence where it alternates from 2 and 0, 2 and 0. And we showed that this doesn't converge, right? It diverges, but notice it's bounded though. So it's bounded, but it diverges. It diverges, right, because it's alternating between 2 and 0. There's not a static value that approaches, and but yet it doesn't tend to positive or negative infinity. So this is a divergent sequence, or where it doesn't diverge to positive infinity or negative infinity. So that leads me to the next definition, which is going to be called properly divergent. Essentially, properly divergent means the sequence does converge to either infinity or negative infinity. Specifically, if it goes to positive infinity, then for all real numbers, capital M, there exists a capital N, so that for all little n bigger than capital N, we have the terms xn be greater than that value, capital M. All right, that kind of makes sense. There comes some kind of cutoff point where then all of the sequence terms are bigger than that sort of value for capital M. Similar for negative infinity, so xn properly diverges to negative infinity if for all capital L, real numbers. There exists a capital N, so that for all little n bigger than capital N, the terms xn are going to be less than capital L. And since that happens for all capital L, then it goes down, like it's going to be going towards negative infinity. All right, so that's what it means to be properly divergent. Note, we know if xn converges, then it's bounded. So the contrapositive is that if xn is unbounded, then it diverges. All right, we don't know necessarily if it diverges to positive infinity or negative infinity. We just know that if it's an unbounded sequence, then it diverges. So then to determine where it diverges as far as positive infinity or negative infinity, you have to use the definition for properly divergent. But that's a contraposition of the statement of if it converges, it's bounded. So if it's not bounded, it implies diverges. So the sequence where it's just the natural numbers n properly diverges to positive infinity. So for any capital M real numbers, there exists a capital N, so that for all capital N bigger, so for any real number, capital N, there exists a capital N such that this capital N is bigger than capital M, and that's by the Archimedean principle. All right, so that's going to always be the case for any real number that we have. So since that's the case, then for all little n bigger than this capital N, which is bigger than capital M, then xn equals n is bigger than capital M. So that just follows from the definition. Here's one for n squared properly diverges to positive infinity. And so we want the sequence xn to be bigger than capital M, which means we want n squared to be bigger than capital M. And that's if and only if we square root both sides, we have little n bigger than the square root of capital M. And again, we invoke the Archimedean principle. So fix any real number m, then there exists a capital N where capital N is bigger than the square root of m by Archimedean principle. Of course, this is meaning that our capital M, though, has to be a positive real number. All right, so for all little n bigger than capital N, which we know capital N is bigger than the square root of m, then that nth term of the sequence, xn equals n squared, is bigger than capital N squared, and capital N squared is bigger than capital N. So that properly diverges to positive infinity. So I figured I would discuss that first before going into the monotone convergence theorem. All right, so now for proving monotone convergence theorem, right, it's going to be a sequence that is monotone, then it converges if and only if it's bounded. Note that if it's monotone increasing for a sequence, then the limit of that sequence is going to be the supremum of the terms, or the sequence properly diverges to positive infinity. But if a sequence monotone decreasing, then the limit's going to be the infimum of the set of the terms, or it properly diverges to negative infinity. So here is the strategy. So we're going to have the sequence be monotone. And I'm going to treat it in two cases. All right, so it's either monotone increasing or monotone decreasing. Let's suppose it's increasing. All right, if it's increasing, then we know that if xn is unbounded, then xn, the sequence diverges. Right, that's something that we know based because of the contraposition of if a sequence is bounded, then it converges. So we're going to show that it's unbound. Since it's unbounded, it's going to properly diverge to positive infinity, because for all capital M bigger than 0, there exists a capital N such that for all little n bigger than capital N, we have xn being greater than capital M. All right, so, but we know the sequence is monotone increasing. So for all little n bigger than this capital N, the term xn is always going to be bigger than the term x subscript capital N, which is that itself is bigger than capital M. So therefore, sequence xn properly diverges to positive infinity. Okay, so that's just using what we know for unbounded and what we know for properly divergent. Now, if the sequence is bounded, and we're dealing, again, xn's increasing, so we have the set of the terms. It's also bounded because the sequence is bounded. And specifically, that set's going to be bounded above, right, because it's increasing. So there's a supremum by completeness. And for this supremum of the set of the terms, let's call it x. All right, so we need to show that the sequence converges. So we show that xn converges to this value, capital X, which means we need to show for all epsilon bigger than 0, there exists a capital N such that for all little n bigger than capital N, the distance between xn and x is less than epsilon. but we know x is the supremum, so we can use the analytical definition of supremum, which states the following. U equals the supremum of some set S, if and only if, for all epsilon bigger than 0, there exists an element S from the set S, where S is bigger than U minus epsilon, basically stating that U minus epsilon is not an upper bound. Okay, so we're going to use that definition. And we can say that there exists a capital N, so that for all little n bigger than capital N, we have xn greater than x capital N, which itself is greater than x minus epsilon, right? Because we're using the analytical definition of supremum. So, and we also know that all xn is less than or equal to capital X, right? That's our supremum. So we can state that capital X, I guess this could be technically should be bigger than or equal to xn, and xn is bigger than x capital N, since that's the index value that and it's increasing sequence. And the little n is a term that's beyond x capital N, so it's going to be bigger than that. And then this x capital N is bigger than x minus epsilon, because we're using the fact of that capital X is the supremum. So we can state that x minus epsilon is less than xn, and we know xn is less than or equal to x, our supremum. And certainly x is going to be less than x plus epsilon. So then we have x minus epsilon less than xn, which is less than or equal to x, the supremum, and that's less than or equal to the supremum plus some epsilon. And then just sort of narrowing the inequality down to x minus epsilon less than xn less than x plus epsilon, we can then say that the distance from xn to x is less than epsilon. I mean, really that's the proof, but I'm going to show the proof now. It's pretty much this, but in shorter, just written more concise. All right, and that's for the case in which xn is increasing. And then I'll talk about how to do the proof for decreasing in a second. Okay, so let xn be a monotone increasing sequence. That is, x1 is less than or equal to x2 less than or equal to ... and xn is less than or equal to x of n plus 1 and so forth. Case I, let's suppose the sequence xn is not bounded. Then for any capital N bigger than 0, there exists a capital N where x subscript capital N is bigger than this any value m that's a real number. But we know the sequence is monotone increasing, so we know that for all little n bigger than this capital N index, we have the term xn is going to be greater than or equal to the term x subscript capital N, which is greater than m. So that means the sequence xn properly diverges to positive infinity. All right, so again, if it's not bounded, it diverges. We're dealing with an increasing sequence, so we showed that if it's not bounded and monotone increasing, then it properly diverges to positive infinity. Now let's suppose it's bounded. We wish to show that the sequence xn converges to some value x in the real numbers. Since for all n, xn is bounded, then the set of the terms consisting of the sequence of xn is bounded above. Then by completeness of the reals, the supremum of this set exists. And I'm going to let capital X to be this supremum. So given epsilon greater than 0, by analytical definition of supremum, capital X minus epsilon is not an upper bound for this set of xn's. meaning that there exists some capital N where x subscript capital N is bigger than this x minus epsilon, where x subscript capital N comes from the set of xn's. But we know the sequence is monotone increasing. So for all indices n bigger than capital N, we know that xn is greater than or equal to x subscript capital N, which is greater than x minus epsilon. And we know since xn is less than or equal to x, because x is the upper bound, because it's a supremum to the set, then we can state x minus epsilon is less than x subscript capital N, and then that is less than or equal to x subscript little n, right? Because it's increasing sequence. And then we know xn is less than or equal to capital X, since that's an upper bound. And we know capital X is less than capital X plus epsilon. So therefore, we have x minus epsilon less than x subscript little n, which is less than x plus epsilon. So we can subtract x and get negative epsilon less than xn minus x less than epsilon, which is the same thing as saying the distance from xn and x is less than epsilon. So thus we've shown that the sequence xn converges to x, where x is the supremum of the set of the terms from the sequence xn. And that was for when the sequence is bounded and monotone increasing. All right, that's the proof for that one. The second case is we need to show that for decreasing, we're going to get the infimum as the limit, or it goes to negative infinity. So now, let's take care of the case where xn is monotone decreasing. Let's take it. All right, and just like how I did in this proof, where I broke it up into two subcases, I'm going to do the same for here. Let's suppose it's not bounded. Okay, so what is that going to mean? So when we did the proof for this case, we said for any m greater than 0, we have a capital N where x subscript capital N is greater than m. So for the other direction, it's going to be any m less than 0. So for any, I'll just call it L. So for any L less than 0, there exists a capital N where we have the term xn to be less than this value L. All right, so that's the equivalent of this when it's not bounded going to negative infinity. And we know the sequence is monotone decreasing. So since this is monotone decreasing, we have for all n, little n, bigger than capital N, x subscript little n is less than or equal to x subscript x capital N, which is less than L. Right, so again, so decreasing so you have like x1 greater than or equal to x2 dot dot dot, and then eventually get to some point where it's x subscript capital N, and then x subscript capital N plus 1, and then keeps going like that. And then so any of these have indices that are more than capital N. So these have indices little n bigger than capital N. All right, and it's just written so that I have it sort of going as less than or equal to for the inequality. But you see that that's the term x subscript little n is the term after x subscript capital N. But what that value is for that term, it's going to be less than or equal to the value of the previous term because it's a decreasing sequence. Okay, so that means we have that the sequence properly diverges to negative infinity. All right, that's what we showed here. All right, now we're going to suppose xn is bounded. All right, and we know it's monotone decreasing, so since xn is bounded and monotone decreasing, so it's monotone decreasing. We have that there's some real number m. I'm calling it little m. So that for all little n bigger than or so that for all the indices where this is going to happen, for all n for our sequence for the indices, we have that n is less than or equal to every an or xn, sorry. Okay, so then if we have this set, this means the set collecting all the terms in a set, xn is bounded below. So that by completeness of the reals, there's an infimum to this set. There exists an okay, and let's call it L. Now we want to show then, right, the sequence converges, and I'm going to claim that that converges to this value L, that is the infimum. So we want to show the sequence xn converges to L, which is equal to the infimum of the set of the xn's. That's what we want to show. So we're going to use like the analytical definition of infimum, just like we use the analytical definition of supremum. So let epsilon be greater than 0. Since capital L is the infimum, then L plus epsilon is not a lower bound to the set. So that means we have some capital N where X subscript capital N is going to be less than this L plus epsilon. Okay, so then we know our sequence is decreasing. So for all little n bigger than capital N, we're going to have x little n bigger than or equal to x capital N, which is bigger than L plus epsilon. I'll make sure that's all. I need to split these, sorry. This needs to be less than. All right, because it's decreasing. All right, that's what it should have been. Okay, and we know L is the infimum. And that means L is going to be less than or equal to x n for all n. And we know L minus epsilon is less than L. So we have L minus epsilon less than L, less than or equal to x n little n, which that's less than x subscript capital N, and then that's less than L plus epsilon. So therefore we have L minus epsilon less than xn less than L plus epsilon. And that's going to be if and only if we subtract L. So we have negative E less than xn minus L less than E or epsilon. And that implies we have the distance, absolute value of xn and L to be less than epsilon. So thus our sequence xn converges to L, where L is the infimum of the set of the terms of xn. All right. So this completes the proof. This was the case when we had monotone decreasing, and we showed that when it's bounded, it converges to the infimum. And then the proof before was dealing with monotone increasing. If it's bounded, then it's going to converge to the supremum. And then we also showed that when it's not bounded, it has to be properly divergent when it's a monotone increasing sequence or a monotone decreasing sequence. So that's where I'll stop it for this video.